Tensions are rising between two powerful nations, each trying to outmaneuver the other in a high-stakes game of intelligence. In the middle of this standoff, a coded message is intercepted. It's a message that could change everything. The usual cryptographers can't crack it. The code seems unbreakable. Enter a lawyer and a self-taught cryptanalyst with an unmatched gift for spotting hidden patterns. Someone who's built his mathematical skills on sheer curiosity and relentless practice. As he starts decoding, line by line, something astonishing comes to light. This revelation could shift the entire balance of power. Welcome to Math Science History. Today, I'm sharing the story of Francois Viete, a lawyer, advisor, and self-taught mathematician. You will learn about cryptanalysis and his founding mathematical applications that are the foundations for today's algebra. Hi, I'm Gabrielle Burchak. I'm an author and speaker with a background in math, science, and journalism. By the time you are done listening to today's story, you will know so much more about this genius codebreaker, the intersection of mathematics, cryptanalysis, and the foundations that lead us to today's mathematical applications. In the year 415, the infamous philosopher and mathematician Hypatia of Alexandria, Egypt, was savagely murdered by church monks. This murder shocked the Roman community and its government leaders. Hypatia was known far and wide as a respected philosopher, mathematician, government advisor, and a professor. Hypatia, The Sum of Her Life, is a book that I wrote that looks not just at the circumstances surrounding her death, but also at the sum of her entire life. I weave in the details of her education, disciples, Neoplatonic philosophies, female contemporaries, and the many mathematics that she wrote and taught about. There is truly more to Hypatia's life than her death. Hypatia, The Sum of Her Life, written by me, Gabrielle Burchak, is now on sale on Amazon. Buy your copy today. In 1589, France was gripped by unrest. Protestant King Henry IV faced constant threats from Catholic Spain, led by King Philip II, who supported French Catholic forces, heightening tensions. Amidst this turmoil, a coded Spanish letter was intercepted, but its cipher baffled French cryptographers. Enter Francois Viete, a renowned mathematician. When he took on the cipher, he noticed recurring patterns, applying algebraic techniques to unravel the message. His efforts revealed a correspondence between Philip II and his generals, detailing Spanish plans to back French Catholic factions against Henry IV. Viete informed French officials, providing them with crucial intelligence to counter Spain's moves. In a bold step, Viete published his deciphering work with the king's consent. However, before even bringing it to the king, he shared the intelligence with the Catholic League's leader, Duke of Mayenne, realizing that Spain's support for French Catholics aimed to divide France. Viete knew secrecy was crucial, as the Spanish would develop more complex ciphers and their code was cracked. Soon, he was overwhelmed with dispatches, enlisting secretaries to manage the influx. His purpose for alerting both sides of the opposition within France was to preserve the dissolution of France. Philip II was furious and accused Viete of sorcery, even appealing to the Pope for excommunication. Yet Viete's achievement wasn't magic. It was an early triumph of cryptanalysis, demonstrating the power of analytical thinking. Viete's success marked a turning point in the French Wars of Religion, weakening Spain's influence. The intelligence he gathered hindered Spain's efforts to control France and helped lead to the Treaty of Vervins in 1598, which ended open hostilities. This conflict, fueled by deep Catholic-Protestant tensions, began in 1562 and persisted through decades of violence and foreign intervention. Henry IV's conversion to Catholicism in 1593 and the 1598 Edict of Nantes, granting Huguenots religious freedom, temporarily eased tensions. However, The edict's revocation in 1685 reignited persecution until the secularism of the French Revolution established lasting religious tolerance by the 18th century. Viète's work showed that intellect could shape the fate of nations, laying the groundwork for modern cryptography and a new kind of warfare. François Viete, born in 1540 in Fontenay-le-Comte, France, was a mathematician and lawyer celebrated for his pioneering contributions to algebra and cryptanalysis. He studied law at the University of Poitiers, quickly establishing a reputation for his analytical skills, which led him to serve as an advisor in the French royal court under both King Henry III and King Henry IV. Despite his success in law, Viète's primary passion was mathematics, where he introduced revolutionary symbolic notation that laid the foundation for modern algebra. His work, bridging law, mathematics, and cryptography, showcases him as one of the Renaissance's most interdisciplinary minds. In addition to his contributions in algebra, Viète was known for his cryptographic skills, notably during a time of heightened tensions between France and Spain. His systematic approach to breaking the Spanish ciphers demonstrated his algebraic insight and pattern recognition skills, which are also used in law. For example, he analyzed redundant symbols in coded letters, identified repeating patterns, and utilized frequency analysis, a statistical technique that involves recounting repeated elements to uncover hidden information. His careful analysis extended to trigrams and digrams, patterns of 2 and 3 letters, helping him identify meaningful symbols and decode the messages. These methods, although straightforward, were innovative for their time and emphasized Viète's analytical prowess, as he essentially laid the groundwork for modern cryptographic analysis. Viète's approach to deciphering was a method of breaking down the code, using his algebraic insights to look for patterns and frequencies in the symbols. He substituted letter combinations and identified repeated patterns, a precursor to modern cryptographic analysis. This mathematical approach, coupled with his patience and logical skills, gradually cracked the code's structure. In a 1997 article titled Secrets, Symbols, and Systems, the author, Peter Pesek, describes Viète's methods, as noted in Viète's memoir before he passed away. First, Viète looked for redundant symbols. As in the case of the Spanish letter, he compared different copies of a letter sent by an ambassador. By comparing the two, he was able to find redundant symbols. Then he looked at the values that were presented in the document. These are known as, quote, essential numbers. They represent the number and are not coded symbols. However, he could then look at the wording around those values. Pesek explains that these essential numbers allowed cryptanalysts to find the words between them. He gives the example 12, M38, 13, where M38 is flagged by the numbers 12 and 13. As a result, Viète realized that the code M38 represented the Spanish word ou, O-U, which means or. Thus, this would change the phrase to read 12 or 13. Viète then looked at conventional phrases that were used in Spain and often used in their literature, such as copia de and memorial y instrucción. These phrases usually indicated that a code would be nearby that he could decipher. Viète then utilized frequency analysis. In statistics, frequency analysis is a method that counts how many times events or values occur within a dataset. Identifying these patterns and trends allows the cryptanalyst to determine whether the frequency of those phrases or letters is used more than they normally would. Usually, this would then indicate that there is a code within those patterns. Viète realized that the succession of the 3 consonants rarely occurs in French, Spanish, and Italian, so he utilized trigrams, which means if you had 3 letters and 2 were consonants, the 3rd letter would be a vowel. He'd find a group of mutually exclusive triads from the text where each would contain a vowel, and those vowels would lead to another code when extracted. This is what Viète coined his, quote, infallible rule. This process wasn't just mutually exclusive to 3 letters. Then he looked for digrams in addition to trigrams. He looked for the succession of 2 repeated letters. These are also known as digrams or dyads. All these methods utilize a monoalphabetic cipher, a simple cipher involving letters and numbers. However, ciphers can also include symbols or use numbers or letters as symbols. Viète's method wasn't founded on intuition or insight. It was a simple, systematic process. Viète had created a straightforward cryptanalysis process that utilized the same practices repeatedly. Viète's mathematical thinking and his contributions to cryptography are intrinsically linked through the principles of analysis, abstraction, and systematic problem solving. The parallels between these two fields highlight why Viète was uniquely qualified to tackle cryptographic challenges during his time. His methods also highlight the power of interdisciplinary thinking. He was a lawyer and a legal advisor. Yet the process of analytical thinking and his ability to break down complex problems into simpler components allowed him to approach the Spanish cipher with a systematic mindset. And for attorneys or anybody who has watched Law and Order, sorry, The Practice, Suits, or any other legal show, you would know that attorneys look for patterns and structures in behavior and outcomes. They would then use that analysis to defend their clients. Likewise, mathematics is often about identifying patterns and structures, which lends itself to cryptography. Viète's keen eye for patterns translated seamlessly to his work in deciphering codes. Furthermore, logical reasoning is foundational to law and algebra. Viète's methodical approach to algebra involved forming hypotheses, testing them, and refining his strategies based on results. This logical reasoning is equally essential in cryptanalysis, where one must evaluate different substitution methods and validate their effectiveness against the encoded message. Now I'm going to go into Viète's algebraic methods. Before Viète's contributions, algebra lacked a standardized symbolic notation. So mathematicians often used words and lengthy phrases to describe operations and relationships as far back as 1000 BCE, when rhetorical algebra was implemented. Known quantities were typically expressed through phrases, and unknowns weren't consistently represented with symbols. By 200 CE, syncopated algebra was implemented, as presented by Diophantus and Brahmagupta. In syncopated algebra, symbolism was used, but it didn't include all the applications of symbolic algebra. Solutions relied on specific rules for each type of problem, often tied to individual cases. For example, subtraction could only be used on one side of an equation in syncopated algebra. These approaches made it challenging to generalize or systematically manipulate equations. For more information on Brahmagupta, I did a podcast on him, and you can listen to that in one of my earlier podcasts. I believe it was episode number 35. And if you want to read the transcripts, you can come to mathsciencehistory.com. Oh, hey, and while you're there, please click on that coffee button and buy me a cup of coffee, because truth be told, they're not really cups of coffee. They are donations that help support this podcast and keep it up and running. Every donation that you make to Math Science History helps significantly. And in case you didn't know, I produce my own podcast. So the money goes towards equipment, computer storage, editing, headphones, and the time I spend deeply researching these podcasts. I love doing this, and I genuinely love those who continue to support me. Thank you so much. But if you haven't made a donation yet, come on by mathsciencehistory.com. There's a wealth of math and science history stories and information, a link to my book, Hypatia, the Sum of Her Life, and of course, that coffee button. So come on by and buy me a cup of coffee. Okay, now back to Viète. His groundbreaking work provided algebra with a solid foundation, marking the end of medieval algebra's procedural roots from scholars like Al-Khwarizmi. By creating symbolic algebra, Viète claimed that this innovative approach could solve all problems. This is a bold but true assertion known as nulum non problema solvere. His approach laid the groundwork for modern algebraic methods and symbolized a shift toward universal problem solving in mathematics. In his dedication of isagogy to Catherine de Parthenay, Viète introduced his revolutionary approach, referring to it as new. He believed algebra had been degraded by earlier interpretations and sought to restore it through a new vocabulary free from unnecessary technical jargon. His work emphasized clarity and order, presenting his ideas as the first steps in what would eventually be perfected over generations. Despite his innovations, Viete lacked a few modern notations, such as multiplication symbols and the equal sign introduced by William Outred and Robert Ricord, respectively. Regardless, Viete's symbolic choices were distinctive, using consonants for parameters and vowels for unknowns, following the stylistic precedent of Petrus Ramus, a contemporary who used similar notation in geometry. This notation, however, did not gain popularity with later mathematicians, including Descartes, who chose other methods. Additionally, Viete continued the classical practice of treating quantities like lines and surfaces rather than abstract numbers. This choice complicated his work and required him to verify his results geometrically. Viete's work, The Analytical Art, published in 1591, introduced the use of letters as symbols for known and unknown quantities, revolutionizing algebra. Before Viete, mathematicians relied heavily on verbose language and numerical methods, as I noted before, without a systematic notation for operations. By allowing general formulas and abstract manipulation, Viete's notation transformed algebra into a universal language for solving complex problems. His method provided a framework that allowed for precise symbolic manipulation and was a foundation for what we now call symbolic algebra. This leap in mathematical thought marked a shift away from medieval practices and set a new standard in problem-solving approaches. The legacy of Viete's algebraic methods went beyond notation. He introduced the binomial formula and developed what are now called Viete's formulas, which relate the roots of polynomials to their coefficients. This was a key development in algebraic theory that simplified solving polynomial equations. His innovations in trigonometry, particularly with Viete's formulas, allowed mathematicians to extract information about polynomial roots without fully solving them, a precursor to later techniques in polynomial analysis by mathematicians like Blaise Pascal and Isaac Newton. Viete's use of letters for knowns and unknowns allowed for broader, more abstract manipulation, and this set the stage for algebra as a generalized and systematic branch of mathematics known as symbolic algebra. Viete's formulas are a bit like reverse engineering a recipe, where one can deduce ingredients, or in this case, solutions, based on the observed outcome. For my non-math audience, Viete's formulas are a set of equations that, when evaluated through his methods, allow you to find data about the roots without fully solving the equation. It's awesome. For example, imagine that you have a recipe that uses two primary flavors when they are combined. Let's say the ingredients are paprika and garlic, two of my favorites. When you taste them, you don't know how much garlic or paprika went into the meal. Still, you can taste garlic's biting taste and the paprika's sweet, peppery taste. Viete's formulas are like a way to reverse engineer that recipe. So, when you see a polynomial, Viete's formulas help us break down how much of each ingredient, or in this case, each solution, contributes to the whole equation just by looking at the numbers in the equation. So instead of tasting paprika and garlic, we're looking for the flavors of math, which are the sum and the product of the roots, otherwise known as solutions. Viete's formulas help us figure out the hidden ingredients without directly solving the equation. For my math audience, in most simplistic terms, Viete's formulas are a set of equations that relate the coefficients of a polynomial to sums and products of its roots. There's so much more to explore with Viete's formulas, and if you love math like me, it's easy to get lost in them. You can explore the interwebs for so many different explanations, but one of my favorite explanations is one on YouTube through the channel called Prime Newtons. Be sure to check out that video because I think this gentleman Newton explains it phenomenally. Viete's contributions even extended into algebraic geometry as he explored ways to construct algebraic expressions using only a ruler and a compass. In his work, A Canonical Review of Geometrical Effects, One of his forward-thinking ideas was the principle of homogeneity, requiring that all quantities in an equation share the same dimension, which would later be a cornerstone of dimensional analysis. His methods in symbolic calculation, especially his three-part process in solving equations, known as zetetic, poristic, and exegetic, streamlined complex problem-solving by breaking equations into systematic phases, a method that would become an enduring tool for future mathematicians. Viète's influence wasn't limited to France. His reputation grew when he famously solved a complex mathematical problem posed by the Dutch mathematician Adriaen van Roomen. At the encouragement of King Henry IV, Viète provided an elegant solution, impressing van Roomen, who traveled to France to study with him, initiating a collaborative friendship that illustrated Viète's wide-reaching impact on European mathematics. In the broader historical context, Viète's work marked a definitive end to the ad hoc rules and verbal descriptions that had dominated algebra from medieval times. His symbolic approach presented algebra not only as a procedural tool, but as a structured, logical system. By introducing abstract reasoning and emphasizing symbols, Viète's contributions were foundational to algebra as we understand it today. His influence was profound, paving the way for algebraic methods used in modern mathematics and cryptography, and his interdisciplinary genius continues to be celebrated centuries later. Viète's rigor and imaginative synthesis of algebraic and geometric principles continue to inspire mathematicians, cryptanalysts, and computer scientists. For me, the story of Viète represents the ultimate in interdisciplinary thinking and applications. So many schools raise our kids to be specialized without even considering the value of embracing multiple branches of learning. By embodying a spirit of inquiry that bridges various disciplines, his legacy reminds us how innovative approaches can advance society, climatology, technology, and security in our increasingly digital world. Viète showed the world that you don't even have to be a scientist or a mathematician to change the future of STEM. Over 400 years, François Viète and his work remain a testament to the power of abstract thought, symbol manipulation, and rigorous methodology that inspire the continuous pursuit of mathematical discovery. Until next time, carpe diem. Thank you for joining me at Math Science History. Please remember to subscribe to the show. Also, if you could please leave a rating or a review, it would be really appreciated. Because those ratings and reviews really do help to increase my listenership, which help to get me more sponsors, which help me keep the podcast up and running. If you want to learn more about the history of math and science, please visit me at mathsciencehistory.com. If you like what you're listening to, and if you like what you're reading, please feel free to click on that coffee button and buy me a cup of coffee. Every cup of coffee that you buy helps me pay for the expenses that go into making this podcast. Also, if you're interested in leaving me a comment or chatting with me, you can always find me on your preferred social media platform, including X, Instagram, Facebook, LinkedIn, Goodreads, TikTok, Threads, etc., etc., etc. Just go to Google and search for Gabrielle Burchak. You can find me everywhere. Until next time, carpe diem.